everyone, my name is Almog. I'm a four-year PhD student at Gauriot, the next program, keeping the Northwestern streak alive. So I'll present some work I have with Romain, Lionel and Daniel Martin on AI Oversight. So I'm not gonna have this slide telling you how good AI is now, but a lot of predicting tasks. But I'm gonna go straight to how we can work better with AI. And there's been a lot of interest in using AI in recommendation systems to probably overcome mistakes and biases. And there's examples in the literature already of situations like hiring and recruiting radiologists. We have judges in pretrial courts. We have even in baseball. And there's a problem. These results are not very promising. We've seen that a very important skill that AI recommendation systems requires is human discretion. Humans need to know when to follow AI advice and when not to follow it. And it's very hard to exercise, and it also can be very slow. So what we are suggesting today is there might be situations where AI could fix apparent human mistakes. And we're already seeing that in the real world. Like we have, when you get out of your lane, when you're driving, the car will automatically steer you back. It's not going to ask you whether you want to go back. We have examples in financial trading, energy management. We have a very recent example in the literature about how managers in fashion can know more about trends and how to price products, but usually they also have some biases. So a human making pricing decisions, but then an algorithm that can block some of those will actually be the best case scenario in these situations. What we're suggesting now is a big change. We want to shift final decision rights to AI. And what this implies is that, at least in those situations, AI has to be very good. We don't want to be overruling humans if we are not sure that AI is, on average, or at least drastically better than humans in those situations. But why would still we have humans in those situations if AI is already good? Well, there's many reasons. Okay, so humans could perform better in some situations, like having private information, like in the example of setting prices in fashion trends. They might understand the context, edge cases. With changing circumstances, the AI might not be as good. But if we're going to have AI correcting humans, we need to be a very apparent mistake. There's other reasons why we still have humans, like social reasons, the traditional fairness, ethical considerations. We have labor market concerns. It's not easy to get rid of humans just tomorrow. And as AI improves, likely to consider AI oversight for more and more settings. Like in this setting we're going to explore today, we are not going to discuss how things differ between AI and human monitoring, but we're going to provide an example of a situation where AI provides monitoring in a place where humans could not provide it. So AI is expanding the scope of situations where we could monitor workers now. To understand how good it is to have AI oversight, we need to understand how humans change their decision-making when they are under this monitoring from AI. And before, with AI recommendations, the main force was exercising discretion. That force changes a lot now. We care about shame, pride, embarrassment, and stress now. Like there's a new whole set of emotions involved and skills. So the question I want to try to solve today is, how did professional tennis umpires respond to the implementation of AI review systems, which is known as Hawkeye? The two specific questions I want to look at is, was there an attentional response? Are they going to put more effort, less effort once their mistakes could be corrected in public? And is there going to be an emergence of new asymmetries? This unique context in tennis, I will explain further a little bit now. It has many practical advantages, and asymmetries, maybe it's not as important in tennis, but understanding asymmetries is very important in other contexts like judges and doctors. The type of errors there are very, very different. So what we do here is provide the first field evidence that AI oversight can change how humans make decisions. Okay, let's very quickly go over the context. In 2006, Hawkeye officially started being used for the first time in professional tennis. Hawkeye can track with multiple cameras, make a prediction, a very precise prediction of the whole trajectory of the ball, accounting for the speed, the spin of the ball. It can make a very precise prediction of where every single ball bounces in a match. The average error is 3.6 millimeters. It's almost nothing. Like the whole ball is 67. So as the ATP, the tennis organism, we will consider Hawkeye as ground truth. For these purposes, they do as well for tennis matches. And what we're going to assess is the collective performance of the whole umpire crew. We cannot disentangle which of the umpires calls each ball. But the way it works is there's 10 umpires, one chair umpire, and then there's one umpire for every single line. So the line judges, all they care about is focusing on one line. That's their whole job. So that's pretty nice, actually. Why tennis? Okay, so we think this is the cleanest context to explore this question. This is a really nice empirical setting. First of all, it's a pioneer application of modern AI for oversight in work settings. Like this is from 2006. We're already 20 years almost since this started getting used. There's great data, and more importantly, there was a testing period for broadcasts. So we have data of 7 tournaments of where every single ball bounced, where there were no challenges. So that's pretty amazing, actually. And we have a lot more tournaments where there were challenges allowed. There's no clear source of prior information, which is usually a big concern in contexts like judges or doctors. And the decision problem is the best we could have. This line judge is basically paying attention at one line. There's a binary state, a binary decision. The ball can only be in or out, and the ball has to be in or out. There's no simpler decision problem than this. Okay, how it works actually is that if a player considers that the umpire made a wrong call, they will just ask for a challenge. There will be a replay in the screen, and if it shows to be wrong, then it might be actually corrected, or the point will have to be replayed depending on the circumstances. So what are the two forces that Hawkeye provides us to study? First of all, are they paying more attention or not? Like one could say that if you have AI monitoring your decisions and correcting your mistakes, there's an incentive to free ride on this technology and you could relax. But on the other hand, you could also be more attentive, knowing that some of your mistakes will be exposed in public, in front of the whole stadium and everyone. So it's not clear in what direction this could go. And second, do we see a distortion in the type of errors? Something very important here is that before Hawkeye, it was not clear whether it was one type of error was different than another one, like saying something was in when it was out or the other way. Those two were very much the same. Right now, it's not the case. If you call a ball in when it was out, then you can challenge. And then if it was correct that the challenger was calling the right challenge, then you just overturn the call and that's it. You can implement the right outcome. What cannot happen is if the umpire by mistake says the ball was out and the umpire said in, you stop the point in the middle. There's no way of going back. So this introduces a lot of controversy into the game, and the umpire needs to arbitrarily decide whether the point needs to be replayed based on the player, if the player had a chance to reach the ball or not. So it puts the umpire in a very tough situation. Like nobody wants to be making arbitrary decisions here. And I mean, I have here some examples, like very recent examples of how this type of mistake in particular disrupted games. Okay, I'm going to start showing the empirical part of the paper. We are going to use this empirical specification. We're just going to regress whether there was a mistake, an incorrect call, and we're going to have a dummy of whether it was when there were challenges or not, and we're going to control by point characteristic, match characteristics, like we're controlling for a lot of things there. And if we look at the entire sample, we can look, there was a reduction in mistakes, 8% less mistakes. But let's dig deeper, and I'll tell you why. Let's break the sample in 4 ways. The first way is, was it a close call or not? Between 20 and 100 millimeters. That's the not so close calls. And then we're also going to break it in serves and non-serves. Why we do that? Because Well, the distance one is very obvious. 20 and 100 is not the closest, so it's a little bit easier, but still very hard. Why we break serves and non-serves? Because those two are very different cognitive tasks. With serves, it goes faster, which will imply it's harder, but also it has some advantages. The umpires know when the ball is coming, where it's about to bounce, so ultimately it's not clear which one is easier. And if we look at the 20 to 100 millimeters, they get much better. So this hints at actually that they are paying more attention. When they can, they pay more attention. What's puzzling is when we look at very, very close calls, specifically on serves, they get worse. This was very puzzling when we ran into this. Why would they get worse when it's very, very close in serves? Serves are those situations where there's already very close serves are situations where it's extremely hard to get better at. They are already at the limit of their cognitive capacity. So what's happening right here is that we're going to see that the shift in type of errors is driving them to make more mistakes. So in order to reduce the now very embarrassing mistake, they're willing to sacrifice a lot more of the other mistake. And I'm going to show you how that looks right now. So this is the raw data. This is in the x-axis, we have the distance to the line. Everything to this direction is out, everything in this direction is in. The farther is the higher the distance. So it's natural to see a mistake rate with an inverse U-shape, right? So this is how it looked before. After Hawkeye, this shifted to this. There's two things to look at. The red line is mostly below the blue line, so that hints at an increase of attention, but there's the shift in type of errors. They're willing to reduce the costly error at the expense of increasing the not so costly one. And that shift is what actually makes them perform worse in the very close calls. When we control for all the points and match characteristics, this is how the coefficients on the estimated coefficients look like. We can see that on the outside, it looks like an improvement, but in the inside, there's a shift in type of errors that it's not very clear, like if they're improving or not in that region. What drives the shift? So what happens actually is that when the ball is very, very close, they just started calling the ball in more often. Before, when it was within 20 millimeters, they used to call in 42.8% of the time, and now they do it 49%. So on short situations, they just shifted to calling in. I have some other empirical results, but given the audience, I'll spend some time in the structural model of rationally inattentive umpires. So our model is very simple, but I think we're very happy with it. It explores the problem in a very good way. It's very simple as in the empirical situation. Two states of the ball can bounce in or out. There's two actions, the umpire can call it in or out. There's also a probability that an incorrect call is challenged. Not all the mistakes are uncovered. So that's an parameter eta in and eta out. Like those are parameters that we recover from the data, which we know how often a mistake is uncovered. They are zero when there's no challenges, of course. And this is the utility we're going to use. We're going to normalize it to 1 when you are correct, and to this when you are not correct. How this looks like, in the pre-period, this will be 0. And in the post-period, it will depend on a cost, which we call the penalty of being corrected by AI. And ultimately, we want to recover those costs to know how costly for umpires it is to be corrected in public. We use a model of channel mutual information. We will model umpires as if they are rationally inattentive. How it works is that this model gives very good closed solutions, and that's why we use it. We say that the reduction in uncertainty, the difference between the posteriors and the priors, scales linearly in a parameter kappa. But what we do is we extend the model a little bit to allow for 2 different parameters kappa. We are not going to fix that when the ball is in and the ball is out, it's equally difficult to make a good call. And this is motivated by the perceptual literature. We are going to allow for different costs of being correct or paying attention in this with these kappas, which is linearly increasing. We can think of those kappas as the marginal cost of learning. Okay, so the nice thing about using Shannon is that the solution follows this very nice closed solution that's called the invariant likelihood ratio. And something really nice is that we have everything there, both the kappas. We can recover the kappas from the data. We have these gammas are the posteriors. We have the utilities. We can recover the kappa parameters out of the data. And we do that with the first period, with the pre-period. And this is how it looked like. We can recover the kappas using the period where there were no challenges. So now that we know how costly it is to learn in this environment, we can proceed to a second stage. Let's use the period when there was challenges, and let's use the kappa parameters we already recovered in the first period to uncover what were the costs of being corrected in public in this situation. And once we recover those, we have that in the pre-period, it will be equivalent to have a -1 as the cost. Now it's -2. So being corrected with Hawkeye when there were challenges, at least for the type 2 error, is now twice as costly. Like the actions of the umpires reflect that it's twice as bad to make a mistake now when they are exhibiting the big board and they have the players shouting at them and infuriated at them. So to conclude, we see in this paper that the introduction of AI oversight in professional tennis improve umpires' performance in certain aspects of the game. So they improve when there's distant calls and they improve when there's non-serves. So where there was room for improvement, actually, I think it's the public nature in this setting that caused umpires to get better. However, the implementation of oversight may change incentives and give rise to reactions in behavior. What we observe in this case is that umpires are leaning toward the less costly mistakes. Importantly, from the perspective of the umpires, maybe not from the planners of this system. So this is very important. When you introduce AI, you might be distorting incentives for some parties, but not in the best way desired. And we think this is really a new area of research. A lot of studies now are focused on AI recommendation, but we think there's a lot of promising research to be done in AI oversight, in understanding more about how, like having more control on AI and human costs, explore the mechanisms in a better way. So we're excited about keep doing research on this line.